Okay, tonight we have a pre-calculus problem. Find the exact value of this expression. So, whenever we see something like the exact value, that is going to probably hint that if we were looking at the unit circle, we'd be dealing with some of these special angles, okay? And in which case, we can get exact numbers quite readily. Otherwise, we'd have to use a calculator and we'd get a bunch of decimal places, and it probably wouldn't work out exactly. Sometimes it does. Okay, so in this case, we're going to review this in terms of basic pre-calc things. And we were taught with the arc. First of all, you're seeing arc tangent here, and you're seeing arc sine, okay, which is also inverse tangent and inverse sine, and you see it tan to the -1 or sine to the -1. So it's arc tan, inverse tan, and what that's saying is some tangent of some angle gives you square root of 3, and the sine of some other angle, say phi, equals square root of 3 over 2. Tangent, as you know, is typically y over x, in which case we have square root of 3 over 1. And in this case, we have y over r, and so square root of 3 is the y in this instance, and r is 2. We could run these for these two angles. What I'm getting at here is I'm trying to say that this is a cosine of a theta minus a phi. And then that would bring us into some trig identity later that we could use. And it's called a addition or subtraction identities. And in this instance, it's a subtraction identity. So the cosine a minus b, okay, equals some expression on the right. And that's what we're going to head for. We're going to try to turn these a's and b's into the angles that we readily know from the unit circle. So, to start with, I just wanted to go over a small routine here and just prove that these two angles are dealing with the same y's and x's and r's. So I can do that by saying x squared plus y squared equals r squared, the Pythagorean theorem. And now I'm going to get, I know over here for phi, I know that y squared would be square root of 3 squared, okay, equals 2 squared plus x squared. This would be x squared plus 3 equals 4. Minus 3, I get x squared equals 1. X equals 1. Distance is always positive, so it's plus or minus, but it really is x equals plus 1. So over here I'm getting y equals square root of 3, r equals 2, and x equals plus 1. That's what I'm getting. Now let's look at the other angle here, theta. We have x squared plus y squared equals r squared. In this case, we have square root of 3 squared plus 1 squared. Well, this is the same y and x we have over here, so this is going to have to be invariably equal to r equals 2. So in both cases, we have y equals square root of 3, r equals 2, and x equals 1. This may not always be the case, but in this case, for both of these sets of inverse or inverse functions, we're getting the same set of values for the y, r, and x. Okay, so Now, onward to the identity. In the identity, we have this here. Cosine of A minus B equals cosine A, cosine B, minus sine A, sine B. Okay, so here, instead of having, I'm going to set this theta equal to this expression over here, and then I'm going to set phi equal to this expression. And I could use A or B, so it's A minus B. That's fine too, in which case we would get this here from the identity. This is the identity, which means it's always true. There's proofs for these identities. I didn't go over it, of course, but there's books or places you can find it. All right, so we have the cosine of A minus B equals the cosine of A, the cosine of B, minus the sine of A, the sine of B. In which case, I have, this is my A, that is my B. But what is cosine? Well, the cosine of something, of an angle, is x over r. And the sine of some angle equals y over r. But in this case, we have the same y's and the same x's and the same r. So this is going to be merely boiled down to substituting this definition, these definitions, by definition, into our expression, which is the identity that we pulled up. And so a cosine A is really what? X over r. So we have x over r, and the cosine B is x over r, and the sine A is going to be y over r, and sine B is going to be y over r. Like I said, these angles may not always deliver back the same numbers, but in this case today, in this example, it has. So let's see what x is. X is 1, so it's 1 over 2. There you go. R is 2, and it's 1 over 2 again. And here we have square root of 3 over 2. And there we have square root of 3 over 2. And when you multiply these together, I get 1/4 minus square root of 3 times square root of 3 is 3 over 4. So what are we getting here? I think I made a mistake here. I think this is supposed to be plus. Let's check our thing here. Minus is a plus. Yes, so I made a little error here. So this is plus. So what do we get? 3 plus 1 is 4 over 4. And 4 over 4 is 1. Okay, you could check this out with a calculator if you wanted to. You can do the tangent of minus 1. Well, we'll put it all in. So let's see what we come up with. We have here the cosine of the arctan of square root of 3 minus the arc sine of square root of 3 over 2. Okay, let's see what we get here. And if we get, this is your check. In other words, check your work with your calculator, and then you'll be sure to have the right answer. Okay, so I'm in radians. You should be in radians mode. So radians mode on your calculator. Okay. 3 square root. Okay, square root of 3. Okay, inverse tangent. Let's see if we can do this. Haven't done this in a while. Inverse tangent. No, I don't think I'm getting it right. How would I do the inverse tangent on this thing? Haven't used this one in a while. Oh, there it is, inverse tangent. So 3 square root. Okay, inverse tangent. Okay, I get 1.04719. Okay, minus sine. Now let's do the sine. 3 square root divided by 2. Okay. Radians mode again. Inverse sine. I get 1.04719. So I essentially have the cosine of 0. Excuse me, 0 degrees, or 0. And the cosine of 0, if we put that in, plain old cosine equals 1. And 1 equals 1. We checked it. And that's the way this problem's done. Thank you for joining me.